All right, just a walkthrough for Tech Assignment B volumes. All right, so you can work in groups for this one. If you want to work alone, that's fine. Also, once you've decided on your groups, then you tell me who you're working with, and I assign you a block of functions. All right, you see what I have here. This little table has 4 functions. Each group is going to get 4 different functions. All right, so you need a Desmos account. You should already have one from the first unit, but if not, you can make one. You don't get spammed, so Desmos doesn't do that, so that's a good thing. So you don't have to worry about getting unwanted emails, at least as far as I know. I mean, I've never received anything that I didn't want from them. All right, so the video overview that I'm about to do is going to walk you through this one example, and once you do basically what I am about to do, then you create share links. All right, so you'll save the Desmos. All right, so you open mine and you save it in your own account, so your name should appear here, and then you select the share button, share the link, and that gets dumped right into the assignment area on Brightspace. So anyway, the first function here, I'm gonna do a quick zoom in. Oh, I hit zoom in on the wrong thing. Well, I guess that's fine too. I wanted to zoom in for the Word document that I have here. Yours is gonna be a PDF, but I just wanted to make it a little easier to see, obviously. That's the point of zooming in. So the first one, I have arc sine of x plus 1 over 4 on the interval of 0 to 3. We're asked to use the disk method, so we use the Desmos link that has, with respect to the x-axis, right? So axis of revolution, x-axis. So I'd use that first Desmos link, which brings me to this, all right? So I'm just gonna swap out the arc, the function that's there for arc sine. You see, it's when I type it, it thinks that I'm treating A, R, and C as constants, variables, things like that. But once I finish typing in arc sine, it goes from italicized to ordinary font, so it knows that this is an actual legitimate function. Open parentheses, I'm going to put a division bar in, then type my x plus 1. This way I don't have to worry about excess parentheses. Right? It's not an issue in terms of the math of it. It's a little clunky looking. So close it up. If you want to see the rest of this line, you could expand. All right. So this is going to give us volume of disk with respect to x over the interval of a to b. All right. F of x plots the function with respect to x over the given domain, and you can see the diagram. I can zoom in a little bit if I want. All right. So it looks kind of like a cone or a bugle or something like that. All right. So you can investigate. You can play around with some of these coefficients. So if I drag my slider, you see part of the graph disappears. It gets truncated. All right. Same idea here. You'll notice that this line command here is creating the actual solid. So you can see the curve. I'll expand it a little further. That curve corresponds with the arc sine function. Right? This creates the solid when you revolve it, and it only knows to revolve because we're going 2 pi radians, right, around the x-axis. So that's going to give us a full 360-degree turn for every disk along that domain. So all I have to do here, if I want to find the volume of this, is drag the A to 0, because that's the low bound of my domain, right? And drag the B to a 3, and this is my volume. So it's actually very, very straightforward. I'll turn this back on so it looks nice. But that's all I'm asking you to do for this one, right? So at this point, I would save, create my share link, and throw that into Brightspace, and then move on to the next one. All right. The next one, this is a little trickier. So let me close this window out. I don't need it anymore. So the next one is with respect to y. It's disk with respect to y. But you see I've given you a function here that's in terms of x. So I'll write this down and then I'll show you what I'm doing. So this is really saying y is equal to x to the third plus 1. I want to solve for x in terms of y, and bear in mind that this is an x value, and so is this. So those have to get converted over also, right, in order to use that app. So y minus 1 is equal to x to the third. Take the cube root of both sides. And you get y equals the cube root, x equals the cube root, force a habit, of y minus 1. Now if I want these over here to correspond to the new bounds, I would take my g of x and pop in the 0. So 0 cubed plus 1 is equal to 1, and g of 3, which is 3 to the third plus 1 is going to be 28. So my new bounds will be 1 to 28. Right? So on 1 to 28. All right. That's the only part of this that could be challenging. All right. So everything else is just popping it in. So I'm going to do the cube root. Now for that, I'm going to go into this little keypad. Go under functions. I mean, I could raise it to the 1/3 power if I want, but there is a built-in cube root function here somewhere. I'll probably just blow right past it. Where are you? Oh, right in front of my face. That's where it is. All right, so this is 3, y minus 1, and my domain is going from 1 to 28. So 1, let's get over to 1. And 28, now that's not an option here, but I can click on that little end and make it go to 28. All right, so now I can go on up to 28. I can rotate it a little bit so it kind of looks the part. If you go into that little wrench, you see the axes all around X, Y, Z. They're all going from -4-ish to +4-ish. I'm going to make that go from 0 to 28. Well, actually, I don't want to do that. Let's make it go, I'll go -28 to 28, like all around. Yeah, that looks better. Because I want to actually see the entire thing. I only limited it to one quadrant. All right, so this is what the figure would look like. We have our settings, and now we know our volume. All right, so this is another case of that was all there was to it. You know, we had to do a little side work, but it wasn't too bad beyond that. All right, so save, share, create that share link, and pop that into Brightspace. All right, the next one is a washer. And we're looking at the arcsine function. So basically the two functions we started with, all right? So let me get rid of this. This is washer with respect to the x-axis, all right? So just make sure you select the right link. The first one, f of x, is arcsine, so I'm just retyping. I did not do the thing I told you to do before. So yeah, open up the parentheses, division, x plus 1 over 4. And this is going from 0 to 3. All right, just make sure I typed it in right. Then my g of x is x to the third plus 1. X to the third plus 1, just making sure I typed it in right. Arcsine looks good. Going from 0 to 3. Now it looks kind of funky, right? And that has everything to do with the domain, right? The cubic function, it's, if I just look at, forget the solid for now, just look at the curves themselves. That cubic kind of takes off, right? And it doesn't look like it's mapping to the same domain, but it really is, right? So I look at that one. That's the bugle from the first example, and this one, if I had more room, it would extend higher. So it looks like it only goes that far, but if I go up to, let's see here, well, 28, same idea as the last problem in terms of y. So let's manipulate this, negative 28 to 28. You know, it's kind of hard to see, but it does cover the same domain and range. Now, it is very hard to see. So let's bring it in on the x-axis, right? So let's go down the line here. We don't need to go out that far. So let me say like negative 5 to 5 on just the x. See what that looks like. That's a whole lot better. So we got the y, we did it all around. The z, same idea. That's the top down. We needed some height, but it looks like it's covering the domain, all right? And that's what we're going for. So once we have those settings in, we have a good looking graph, and that's part of the assignment, is to have a good looking graph, right? So it's not, I mean, it's simple enough, but it's not as simple as just putting the functions in, sliding the sliders and being done with it. You got to play around with the graph, make sure it looks the part, all right? And if it does, then you have your volume, and save, share link, submit onto Brightspace. The last one's a little trickier. All right, it's the nature of the functions that are involved, but I did go back to functions in terms of y. It's washer method around the y-axis. There's a little trick to it though. Let me show you. Arcsine, we want y plus 1 over 4. Close it up, and then the other one is just y to the third plus 1. Now the issue that we run into here is based off of the domain that's given, right? The domain applies for one function but not necessarily both. So I'll establish the domain based off of what it says there. So let's say 0 to 4. If you look at this one, now in comparison to the previous one, where we zoomed out and we got it to match up, this one actually, it's not going to work that way, all right? Because if I extend, let me actually do it this way. I'll extend this to 5. Actually, let me extend it to 10. So you see that the red graph never expands beyond 4, all right? And that's because if you have a number in here for y that's too big, it'll put it outside of the domain for the arcsine function, right? So we got to be careful about stuff like that, because no matter how far I go, it never extends any further, all right? If I go the other way, it's fine, you know. We get plenty of graph here, but we got to figure out where it's going to stop expanding, all right? And it looks like the one in gray, which I'm struggling to remember why I made it gray to begin with, but you know, let me make that purple. The one in purple, that's polynomial, so that's going to continue on, but the one in red is going to stop. So we have to stop it at the appropriate location in order for this to work out. And you see here, when I expand, eventually it goes to undefined. So we want to figure out what that precise moment is where it goes from good to no good, if you want, all right? So on the low end, we're fine. The 0 is good, and it's working for both. I can turn it around and see that both graphs are kind of living, or I'd say, I don't want to say obviously, but if you zoom in, you can kind of convince yourself that that's the case. In terms of the D value, the moment I go beyond 3, I'm in undefined territory, all right? So we'll just do a quick investigation here. If I make it 3.0001, all right? So you can see that if we go just a smidge beyond, now there is a tolerance issue here, but I'm not sure what I did there. 3 is fine, 3.1 is too much, 3.05 too much, oh 01 too much. So it's a very infinitesimal amount beyond 3 that it's allowed for, but we can just cap it at 3 and be good, because even that infinitesimal amount that still exists, you can see I put in this number here, and we get a value that still exists. If I wipe that out, so we're looking at the difference of, if you look carefully at the volume calculation, when I input the 1 and remove the 1, ever so slight change in decimal value. So once you're satisfied that you're kind of living around the right volume, you can, because this is an approximation technique, you can just cap it at a reasonable location. So these, regardless if I went out a bunch of zeros and another 1, I'm going to get something that's essentially the same. All right. Now I just want to get my graph to look the part. All right. So I need to go, let's see, in the X direction, I need to go wider. So let's do that. If I plug in a 3 to this function, we're going to get that same 28 that we got in the last problem. So I'll go 28 all around and then adjust as needed. Oops, that's not an 8. 28. Sorry, negative 28 to 28. And then we'll bring it in on the Y, right? Because it's looking really smushed there. So all axes, let's change our Y back. Negative 5 to 5 should be okay. And now we have a good looking graph, which should look just the same, just around the Y-axis as the one that we did in number 3. All right. So the trick on this one is getting out far enough that we end up with a volume that actually exists. All right. And since we're only doing this with washer, anything beyond that wouldn't exist. If I said find the volume of the solid, then if I wanted you to use like mixture of techniques, then you could kick over and do the disk method for the rest of it. But that kind of wasn't the intent of this assignment. All right, so once you have a nice looking graph, because again, the appearance of the graph is important, then save, share link, submit.